Okay, so in this file, we want to again get the potential at A minus the potential at B, but we want to choose an arbitrary path, a path of any shape, and show that it doesn't really depend on the path. We know it shouldn't depend on the path, but we can prove it. So we're going to do this integration of E dot dr. Integration of E dot dr, you have to choose a certain path, cut it up into small parts. Here I cut it up into 1, 2, 3, 4, 5 parts, but of course you should cut it up into an infinite number of parts. And then let's see how we can calculate this integration. So this is what the integral looks like. Now in this particular problem, the electric field is uniform. That means this E is just a constant value. It doesn't change from point to point. So I can take this E out of the integration. And so you end up with E dotted into integration from A to B dr. Try to justify to yourself how we took the electric field outside and how these two things are the same. Because the electric field is just a constant, it's a uniform electric field. So we took it outside, the dot product goes outside, and you end up with something which is integration from A to B dr. What is integration from A to B dr? What does that mean? It means you're adding this vector plus this vector plus this vector plus this vector plus this vector. Of course, not only these 5 vectors, but when you cut it up into an infinite number of parts, you're adding those infinite number of vectors. What happens when you add vectors like this, such that the end of one of them is the beginning of the other? What happens when you add these vectors from the point of view of vectors in general? Well, you get a vector that points from the beginning to the end. That vector, the blue vector. That's what this integration is. And so I can replace the integration by that, and I can find the answer then to be E dotted into this vector that points between point A and point B. Now the dot product between any two vectors is the magnitude of the first times the magnitude of the second times cosine of the angle between them. Okay, if I take the distance between A and B, the magnitude, this distance, and multiply it by cosine theta, doesn't that give me this distance? Isn't this distance d equal to this one times cosine theta? Try and check that out and make sure you understand that. Then I can replace r cosine theta by d. And that gives me the same result that we had in the previous two files. The potential difference between A and B is equal to E times d. D is the distance between A and this point here, which is perpendicular to B. So we get exactly the same answer. So the potential difference between 2 points always has the same value, no matter what kind of path you choose. If you go perpendicular, if you take point C to be perpendicular, you go from point A to point C like this, then using that formula, VA minus VC is E dotted into the vector between A and C. But now the angle between the electric field and the vector RAC is 90 degrees. And so you get 0, which is exactly what we expect. Remember, when you move perpendicular to the electric field, there's no difference in potential between any of these points. So the potential at C, the potential at A minus the potential at C is 0. They have the same value of potential. VA is equal to VC. So again, we get this picture where the darkness or the darkness of the red color indicates the value of the potential. So the potential is large when you're at the left part side, and when you go to the right, it gets lighter, gets lower potential. And as usual, the electric field always goes from a region of high potential to a region of low potential. And this is what the problem looks like in 3 dimensions. If you look at in 3 dimensions for this uniform electric field, the surface that has the same potential, they're planes. Any plane that's perpendicular to the electric field has the same potential. So if you go on any one of these planes, this plane for instance, let's say the plane here, the potential is 15 volts. Another plane, the potential will be a lower value because you're going towards the electric field. The electric field goes in the direction from high to low, so you're getting lower and lower values. So this just illustrates what the equipotential surfaces look like for this kind of problem.